Hello, and welcome to Developers Gone Wild. My name is Tim Farley, and I'll be presenting today on the topic of application security. Who am I? I am a principal security consultant with Optiv's application security team. I've been with Optiv for about 4.5 years. I'm based in Atlanta. I'm a former software developer myself, and I developed some security tools with internet security systems and spy dynamics in the past. And from that work, have derived 3 patents in my name. You can reach me while this presentation is going on for questions and answers. And so on the Discord for SourceZeroCon at Krelnik, Krelnik, or on Mastodon at Krelnik at infosec.exchange. So let's talk about developers gone wild. We're going to cover 4 main examples here. Now, obviously, whenever you're talking about application security, you're talking about developers who have made mistakes. And I'm not talking about I'm not going to waste your time talking about simple mistakes that any testing tool can find. And I don't mean to embarrass developers by pointing out mistakes that they made. But sometimes when you do enough tests, you run into situations where it's truly beyond what you've seen before. And we're going to cover 4 main topics. One is rolling your own solution, failing to be a team player, failing to understand the why. This is a big pet peeve of mine is developers who don't understand how things work underneath. And then finally, and I think is the most fun example, it's really a self-inflicted injury caused by a powerful tool. So we're going to do each of those examples. These are all derived from actual tests I was involved in. Of course, I have, anonymized the data. And we will not be mentioning any actual clients or any actual developers during the course of this presentation. The first example is rolling your own. And if you've ever read anything about cryptography, cryptographers always tell you never roll your own cryptography. It's just not a good idea. And it's not a good idea for a lot of other things too. In this example, we're going to talk about JSON Web Tokens, or JWTs. You see these a lot in modern web apps, especially when there are API suites involved. And they tend to look like this. They look like a blob of base 64. They look like an especially long random token in a cookie or in a header value or whatever. And you can spot them easily because of a couple of features here. It's not just base 64, but you'll notice there's a couple of periods in the middle. Period or dot is not a normal symbol that you would see in base 64. So it's actually broken into 3 parts. And 2 of those parts, the first 2 parts, always start with EYJ, lowercase EYJ, and that's because that's what JSON looks like. So if you're, it's a good thing to learn that if you just happen to be looking at a burp log entry or traffic in Wireshark or whatever, and you see something that looks like this, you may be looking at a JWT, even if it's not in a position in the traffic where you would expect them. Now, of course, burp and other tools can automatically detect these things and decode them for you. Now, what is a JWT? Well, it's an idea about doing stateless session management. Okay, so the idea is no state is actually stored in the server. Instead, the key parts about what the user needs to be able to do are encoded right into that token using JSON. And then the token is cryptographically signed using a secret key when the server generates it. So you pass the token down to the client, and the client hands it back to you. And if the signature matches, then you know the token, hopefully, if your key hasn't leaked, came from the server and is legit. And if you take those EYJ parts apart, the first one is a little header that just kind of tells you a little bit about what type of JWT this is. And then the second one, the big one in the middle, has the information about the user. Here's an example that I just made up. With my name, admin equals true, issued at such and such a Unix date time, exp is expired, and that's another Unix date time. The signature at the end is just a binary value encoded into, and what's in it will depend on the algorithm that you've chosen. But none of those details are super important for this example. I was testing an app. It was a facilities management application, and it had a JWT that decoded something like this. And these Optiv users were accounts that were set up for the purpose of the test. I'm not exactly sure why they had so many different ways of displaying the name. That'll come up later as to why that might necessarily be a bad thing. But you notice there's a thing there that says roles, and says that this person is the building supervisor and a building manager, and there's a location indicated. So everything the app needs to decide what to give this user is right there in a JWT. They're the supervisor, they're the manager, and they're managing building 1701. So that gives us all our authorization marching orders right there in the JWT. But there's something missing here, which kind of jumps right out at you if you have worked with JWTs a lot. There's no date in here. There's no when it was issued. There's no expiration information about what this is. In fact, there's no unique information in here at all. If this user's name and roles don't change, this token will be the same every single time they log in, which means that large blob of base 64 will be the same every time they log in. And we pointed this out because it means that if you steal the token, it's the ultimate session fixation bug, because if you steal the token, you can be that user forever. So this was a test where we were going to do a retest. And when we got back to do the retest, lo and behold, the JWTs that were being issued by the server had two new fields on the end. They had a logon time and they had an expiration time. And of course, I then tested that the logon time and the expiration time were actually being enforced, and everything seemed to be working. So I was prepared to give this app a pass. One of the issues we discovered was that the tokens from the previous test, which I still had because the retest was only a few weeks later, still worked. So however I didn't have source code for this test, but however they had written their source code, the check that checked those dates and times checked them, but it didn't check to see if they were there. So if you handed in a JWT that was properly signed and it didn't have a logon date time and it didn't have an expiration time, it was still good. So I had to fail them again, and then they had to fix their code. But one of the things I would point out, and I think I pointed this out to the client, but you don't want to criticize people in the way they write their code. If they want to write code that looks like this, then fine. But a JWT written to the way the specification is written would kind of look more like this. Okay, I'm not sure why they had to have Optiv $user like 4 or 5 times in there. Role and location is the same, but you notice here I've got my issue date is just a Unix timestamp, and it uses the ISS field, and the expiration date is also Unix timestamp, and it uses the EXP field. And, that might rub you when you're reading the JWT spec. You might think, oh, I don't like 3-character variable names, but there's a reason why it's written that way. And the reason why it's written that way is because these tokens are transmitted repeatedly to the server. So you want them to be short. And there's no compression in here. And here's an example, those two versions of that same JWT, look at how much difference it makes in the size of the token. Now, okay, we've got gigabit Ethernet, maybe we don't care about this, but every little thing you can do to make your app run faster is a good thing. So it's something to consider. So what was the impact here? Well, there were no timestamps, which means that every single time you encoded that JWT, assuming the user's rights didn't change, you were going to get the same base 64 encoding. So you could impersonate that user forever. There are also two other fields that I didn't discuss called JTI and NBF. And if you had added those to the JWT, even without an expiration time, you could at least forcibly reject some in certain cases. They're useful for cases where you need to be able to reject a JWT. And then the minor impact of network usage due to longer tokens. So what have we learned? Well, as a tester, you always want to be looking for these things, even if they're appearing in weird places, right? So watch for that EYJ thing. Now, of course, the tools are really good. Burp is really good, especially with certain extensions loaded at flagging up JSON web tokens when it sees them, but you need to be able to keep an eye out because every once in a while people will put tokens like these in a weird place. Keep an eye out for tokens or cookies that are the same value repeatedly, like Tuesday of your test and you get the same cookie you got on Monday. That's something to pay attention to. And if you're doing a retest for a client or for your own company, make sure you keep some notes from your original test because, I had kept some copies of the JWTs that I had used to demonstrate that they were retransmittable and reusable infinitely. I still had them because it was only a month later. Now, of course, once your engagement is shut down, you've got to dispose of the data appropriate per your data retention policy. So, of course, all that data is gone now. I had to fake up what you saw here. But as a developer, the important takeaways here are don't roll your own versions of common standards. Don't try to read the RFC and write code that does what the RFC does. Well, these folks didn't even read the RFC. They read probably a blog post about how JWTs work and didn't understand why there were timestamps in them and why that was important. Every environment has a library or a package or something to handle all these standard things. And make sure you check for missing fields. Check to see if the field is there, because if it's not, something weird may be going on. Our second example has to do with being a team player. A lot of times, especially if you work like I do with corporate applications, the code is written by, large teams of people, and sometimes people come and go so that some of the programmers aren't around anymore, but sometimes they're still around, and you need to be able to communicate with each other and understand what your partners in the project are doing. Now, in this case, you have to understand cookies. Cookies, of course, are a standard thing in web applications. And they are, for programming purposes, a cookie is a very special thing because there's certain rules that are applied to cookies so that we all know how they behave in terms of how they're protected, what types of connections they're transmitted on, whether or not they're accessible to the browser or also to the scripts in the browser, and so on and so forth. And so it's important that we understand these rules and why they're set up the way they are, okay? And we always tell people that any important cookie should, within reason, be set to be HTTP only. And if it's on a secure connection, it should be set to be secure. And there's some other settings you can put on cookies to protect them. In this particular case, this was an application where in a previous test, they had been told that they needed to add the HTTP only flag to the cookie. And they had done that. And so the cookie was, no longer accessible to JavaScripts. And this programmer decided he needed access to the session cookie from the handler that handled the API behind the scenes to this. They were going to do an HTTP post to an API. And lo and behold, he couldn't get at the cookie because it was set to HTTP only. So what does he do? He uses PHP templating within the JavaScript to shove the cookie into the JavaScript so that it's in there as a fixed literal when the page gets issued to the user's browser. So when this form gets pushed up to the server, lo and behold, the cookie's being sent back, not just in the cookie, but also in the form. The problem with this, of course, is this completely subverts the HTTP only protection, because now the cookie is sitting in the form. Or it's sitting in a web page, which means that if we could get a cross-site scripting vulnerability against that web page, we could obtain the cookie even though it's set to HTTP only. So one programmer had completely subverted a important security-related fix that had been done by a different programmer. What is the impact? Well, cookies are protected by this known behavior. HTTP only is there for a reason. Secure is only there for a reason. If you start taking cookies and putting them in other places arbitrarily, they leave the protection of the browser behavior. And so copying a cookie into a web page bypasses the HTTP only protection and undoes the previous fix. So what have we learned? As a tester, be careful and read the JavaScript that you're seeing carefully, because if they're using a mix of the templating language on the server side with JavaScript, weird things could get put into the JavaScript. So keep an eye out for unusually formatted code. And don't assume just because in your setting up for your new test, you noticed that they had fixed this bug before and it was marked as fixed by the previous tester. Don't assume that they really understood why that fix is there, because clearly somebody didn't. As a developer, communicate with your fellow developers, please. If you're on a team and you're working on a large app together and you run into a problem like this, go find the person who made that change and make sure you understand why they made it. Make sure they understand why they made it and make sure you understand their explanation. And that's all part of understanding the overall authentication and authorization architecture of your application. If you don't understand why cookies are the way they are, then you should stop and think and before you work around something like this. So the next example goes to the question why. A lot of times people do things and use tools and develop code, and they don't really understand what's going on underneath and the why. We already had a little bit of a why with the JWT example, but this is another deeper why question. And it has to do with API authentication. Now, if you've ever done an API test, they're all over the place. There's, many, many different ways to handle authentication in APIs. So it always makes it kind of exciting, trying to figure out how to get your tool configured to authenticate itself to the API. And tools like Burp are handy for this sort of thing because you can plug in code. One of these cases was I ran into an API, a small API test, and they were using HMAC authentication. It's kind of a lesser used method, but if you travel a lot in API circles, you will run into it. There's no real standard for it that I've seen. There's no like RFC of if you're going to do HMAC authentication, here's how it works. But the basic idea is that an HMAC is a hash with a key involved. So you're using a secret key to create a unique hash of the request, and then storing that in a header as the request is being sent up. Okay. And the idea there is that, again, if the crypto doesn't work out on the other side, we reject the request. But it does mean you have to distribute a secret key to anybody who's going to call your API. So this is typically, I found, used in kind of business to business situations where maybe you've got 6 or 7 customers or 20 customers that need to use this API, or certain partners or whatever. So the problem of distributing keys to everyone who's going to use the API is not that big of a deal. This is not something you would want to use if you're going to let 1 million people call your API. So we had an API we were testing, and here was an example that it sort of looked like this. I've simplified this and anonymized it. But basically all the authentication stuff was in a standard HTTP authorization header. And we used the word HMAC at the beginning to say, okay, this is an HMAC format. And, they have to do something on the server to handle these headers. But you'll notice there's 4 separate things that are there in the authorization header, which I have wrapped on the screen here, so it's easy to read. There's a client number. That's so that the server knows how to get the appropriate key to use to do the HMAC, right? We have to know which client is calling. Then there's a nonce. That's just a randomized value, and it's to help make sure that the request being sent to the API is not replayable by adding something random. And another thing that helps do that is the date. Okay, in this case, it's a Unix style timestamp, and then we have the MAC, which is a cryptographically generated HMAC value. So there's usually a very specific list of what is included in the HMAC calculation. Typically, it will be the URL of the API that's being called. And if there's a post body, if there's data in the post body, it will include that data. And it will include some of these values from the authorization header, the nonce and the date, typically. Okay. And that's all included in what's encrypted or hashed. Now, like I said, I had to write some code to do this because this client was using a format that I didn't recognize, and my tool didn't know how to handle. So I wrote a burp extension. Actually, I just adapted one that was out on the net and tweaked it up so it did the right format. And when I was playing around with it, I started thinking, well, I wonder if what he's doing with that nonce and the date, what would happen if instead of passing the actual date stamp of now, I passed just a 0 there? And since I had a valid key, I was doing a legitimate test for this client. I had a valid key. I could make a request that was valid, but which the date was 0. And lo and behold, the request was accepted. Because it turned out that even though he was actually including the date in the HMAC, he wasn't actually checking the date on the server. And that's because he didn't understand precisely why the date was there. The date is there for a very specific reason so that you can check it very quickly as the request comes in. And obviously, because clocks are never exactly synchronized, you have to put a little bit of fudge factor in there. And the problem is that especially if you have an API, this particular one was to get a list of updates. And as you can see, it's an HTTP GET call. So it was just a simple call that was going to retrieve a list of new items. And so that's a call that you might really honestly want to retransmit. So you need that date in there, or else you can take one of these calls and just retransmit it forever, right? The hash is always going to be the same because it just has the URL and the other values that are here on the screen in it. So once I have a call that can call that get all the updates API, I can retransmit that call forever again. So if I manage to intercept a little bit of traffic from a legitimate customer, I can look at their data from now until the future, right? Unless their client number gets revoked. So here's the impact of HMAC fields and testing them properly. The nonce and the date stamp are there to combat replay attacks. That's an important role that they're playing. And you need to be checking them, or else you are vulnerable to replay attacks. The server needs to reject requests with invalid dates. Checking nonces is a little more weird because obviously this is kind of going for a more stateless sort of thing. So keeping a list of all the nonces that have been sent, in theory, that would be the correct way to do it. In practice, that's a little difficult, but at least you could check to see if the nonce had at least something in it and not just a zero, or not just the same nonce over and over and over. And the problem is that calls to simple retrieval APIs can be trivially replayable. And that could be a problem. So as a tester, one of the things we learn is test the authentication method of the API. Don't just test the semantic stuff that's going on in the API. Test whether the API itself has been implemented correctly. Because in many cases, folks use a built-in library, like if you're testing a Microsoft Suite app and it's using SOAP calls, typically that's using the Microsoft SOAP libraries. And you're not going to find a lot of problems with that. But if folks have rolled their own with a REST API, which a lot of folks have, you need to test to see if their authentication implementation is actually correct and is actually checking all the things that are in there. And this is another case, like many of these examples, where manual testing, there's just no replacement for it. You can't be an application security tester and just run a tool. You have to be able to get in there and do things manually. As a developer, whenever you're coding something like this, you have to think about why. Why is that nonce there? Why is that date there? And if you understand why they're there, then you can implement appropriate checks. And this will make your API or whatever it is you're implementing secure. But never assume that the data you're being given is legit. Don't assume that just because there's a date field that the client filled in and you wrote the client that it came from you. It's the classic error of be distrustful of everything coming in. And my favorite example is shooting yourself in the foot. We have such powerful tools these days, and folks are so isolated away from the HTTP stack when they're programming that it's very common that folks will do things that are just really, really dumb and not even realize what they're doing. The background for this one, you have to understand hashing passwords, right? Of course, everybody knows passwords should be hashed. You never store a password as plain text. No application should be able to retrieve and display your password to you in a reset email or anything like that. What they do is they store a hash of the password. You can, spend hours talking about different hashing algorithms, but there's years of experience out there, and there's good hash algorithms. You can just, find one that works and has been vetted and use it. And all the platforms have standard functions to do this. Unix has its old crypt function. .NET has what they call the core identity library that you can implement users on a website very easily. PHP also has its own version of crypt, but it also has a very nice function now called password hash that gives you all these different options about what format you're going to store it in. Java has the secure random class. So there's all sorts of great options for hashing passwords. And once you've got the password hash, the only thing you should be doing after that is comparing hashes to that hash, never anything else. So one day I'm testing an application and it was built with .NET framework type, technology. And I see an API call. There's an admin. We were given admin accounts and normal accounts. And I see an API call that's getting a list of users. And this was being done, it was a single page application. So there was an admin menu item and you could get in there and get a list of users so that you could do things like disable a user or, change their password for them or, the typical sysop type things that you would do on a website. And when you went to that screen, behind the scenes, an API would be called and some JSON result would come back from the server that looked like this. And, it has all the typical fields you would see: first name, last name, what role does this person have, should their password be reset, what's their email address, so on and so forth. But one of the things that I noticed, and several of the examples in this presentation have mentioned large blobs of base 64. You see them all the time when you're testing APIs and testing websites. And here was another example. Look at that. It's a large blob of base 64. But I had seen some base 64 blobs like that before, and it sort of looked familiar to me. In particular, the stuff right at the beginning where it was a capital A, capital Q, A. It's like, I've seen that somewhere before. I wonder where I've seen that. Now, I've obfuscated this example a little bit. The field name there, since this is JSON, is just PH. In the actual test, it actually said password hash right there. So I went to the documentation of the Microsoft.NET Core Identity Library, and lo and behold, the Core Identity Library has a way of saying, okay, this table in my database is my user table. I want you to put the appropriate fields in here that you need to manage users. And it stores a blob of base 64. And what's in that blob is actually basically, if you're a C programmer, a struct. Okay, and the struct has like 5 or 6 fields, but a couple of them at the beginning are just little integers that say, is this version 1? Is this version 2? Is this version 3? How long is the thing after this? Where is where is the salt? What algorithm are we using? Where is the salt? Here's the actual hash, and here's the salt. Okay, so you've got everything you need to check that hash, even if it requires a salt, if it requires a repeat count, that's stored in another field in there. It's all right there in one place, okay? And of course, you don't have to know about that. That's all the guts of the Core Identity Library. But the reason that you see the AQAAAA at the beginning is a lot of the fields at the beginning are very small integers, like 0 or 1 or stuff like that. And you typically get a lot of 0 bytes, and that's how it ends up being encoded in base 64. So if you see that pattern, it could well be a .NET Core Identity hash. So I started thinking about, well, it's like, how did they end up with an API that would return the whole user database like that? Because they weren't using the hashes. The screen where you edited users, of course, didn't display the hashes. It displayed a field for password, and all you could do was say, tell the user, you could set the password to a specific value, I think, or you could flag the password so that the user would have to reset it. And that was it. It wasn't really even using those hashes. So it's like, I was thinking about that, and it's like, how did that end up happening? How did they end up building this API that would shovel all this data out at the app? And it turns out that if you're using the standard Microsoft libraries like Core Identity and .NET Core, and particularly the Entity Framework, even a tiny little piece of code like this can result in you having an API just like I described. And as you can see here, there's nothing relating to passwords here. This is just an API that says, hey, I want to be able to get a list of users and do stuff with them, okay? And this particular line of code, this one line of code, is the particular line of code that would create that call, that API call, that would return the entire user file, user database, including password hashes. So literally by writing one line of code, or probably cutting and pasting it from a Microsoft example on their website, boom, you've made this mistake and you are now shoveling hashes out to your app, even though the app is a single page app and it doesn't know how to work with these hashes. And this is a good example of shooting yourself in the foot, because you have these powerful tools that let you build really powerful APIs just using a few lines of code, and letting the frameworks do all the work of turning database field names into fields in the JSON and all that good stuff. And you can't see in your code, if they search their own code for password hash, they wouldn't find that anywhere near this code. So it would be difficult to figure out where the problem was occurring, and it's because the framework is doing all the work for you. A way to combat this, again, is to be aware of what's going on underneath. Like if this developer had actually run a tool like Zap or Burp or Fiddler while running their app, and just watched what happened behind their app, they could have seen this bug themselves, right? It's like, oh, we're on the editing screen. How much traffic did that generate? Screen. They could have figured it out on their own without having to, wait for a security test many weeks later. So, of course, the impact of exposing hashes is kind of dire. Core Identity Library actually uses a really good hashing algorithm, and it's pluggable, so you can actually have it, upgrade to a more powerful hash later if some crypto gets broken or something. But you should never, ever, ever transmit hashes outside the server. They should only be there to sit in a database and rot and be compared to other hashes of potentially matching passwords. And that's it. It shouldn't be sent to other places except maybe a backup tape. And even properly salted hashes with a good algorithm can always be broken, right? It's just a matter of time. So how patient is your attacker, right? Are they willing to spend months? It's easy to spin up a password cracker machine in the cloud now. And if you don't care when you get your answer, just spend some CPU hours cracking passwords that you've stolen using an API like this. And so an attacker can leverage one, minor sysops account on your website into a whole pile of all your users' passwords to potentially abuse. So what have we learned as a tester? Again, familiar looking data, be familiar with common hash formats when you see them, that AAQAA or whatever it was is one. If you look in the documentation for PHP's hashing algorithm, there's a standard format that those hashes are stored in. If you look at some of the cracking tools like Hashcat, they will document a whole bunch of standard formats. And if you see things like this flying around in an API, understand that it might be something important. And, understanding things like the Microsoft Entity Framework and being able to be conversant with those APIs and understand, how did that happen is an important role of the tester. As a developer, you have to be careful with these tools. Like they will cut your arm off if you don't use them properly. Understand how they're solving a problem for you, and occasionally look under the hood. Fire up Fiddler once in a while and run it while your app is running. And if you see a screen that's taking a long time to generate, look in there and see what the traffic is underneath. Maybe you're transmitting way too much data. Maybe you're transmitting data that you don't need back to the app. And you could optimize things in the background. But sometimes you're transmitting data that you should never be transmitting outside the server. So let's summarize all those lessons learned. This was all some great mistakes that were made by anonymous programmers out there. As testers, manual testing is always important. If you're ever hiring an application security tester and all they want to talk to you is about automated tools like scanners, you might not want to be talking to that tester. We emphasize at Optiv manual testing very, very heavily because that's where you find the really good stuff. Keep an eye out for familiar looking data in your tool. If you're looking at your burp proxy logs and you see things that look familiar, dig into them, right? Because you never know what you're going to find in a weird spot. Keep an eye out for tokens or cookies that get the same value over and over. This is another thing that I don't know of a lot of automated tools that would catch that automatically. Keep notes. Keep your data, within the limits of your data retention policy. Obviously, you have to be careful about keeping data beyond the scope of a test. But if you're doing a retest to check fixes, have the logs from the original test handy. Usually it's only a few weeks ago. Don't ever assume that a previous fix was fully understood. Just because it was verified that it's there, it doesn't mean everybody on that development team understands why it was done, and they might end up undoing it. When you're testing APIs, test the authentication method, not just the API itself. That goes for websites, of course, too, but APIs are becoming more and more important, and you have to keep people honest. And understand how these development tools, the more you can learn about development tools and common libraries, React, Angular, .NET Framework, the various Java libraries like Spring and whatnot, the more you can understand about how these apps are put together, the more you can understand about how some of these strange mistakes end up getting made, and you'll become a better tester. As developers, of course, it's true of testers too, but we always need more education. Don't roll your own version of anything. If it's a common industry standard, I guarantee there's already a library for your platform and your language that does what you need it to do. Never assume any data you're being handed is legit, even if it's part of the authentication and highly technical fields. Assume somebody's tampered with it. And because you're assuming that, implement all appropriate checks. If you're being handed a date, make sure that date makes sense. Understand your overall authentication and authorization architecture. There's a reason it's set up the way it is. You need to understand it. If you find yourself trying to work around it, it's like, oh, we have, authentication is preventing me from doing this, so I have to do this tricky thing. You need to stop and think about why you're doing what you're doing. Understand the why of why things work the way they do, okay? Sometimes that means getting down and dirty and looking at packets or looking at proxy logs. But one thing you can do that's always important, even if you don't do that, is communicate with your fellow developers and understand your power tools and be careful with them, okay? Don't just implement something because it was in a Stack Overflow answer or a Microsoft help page. Understand what it's going to do to your application. And always be looking on the wire, because if you don't understand what's going back and forth between the client and the server in your application, then you don't really understand how your application works. All right, I think that covers what I needed to cover. And we will handle questions in the Discord. We may have already been handling questions in the Discord, but you can go over to the Discord and ask me questions today or later today. And you can also reach me on Mastodon. Both places, it's Krelnick, Krelnik. On Mastodon, it's on InfoSec Exchange, conveniently enough. And I thank you for your attention.